Hello, good morning, good afternoon, good evening. Welcome back to week 4 workshop of Mathematics 2023. Today's topic will be on a transfer learning on medical image analysis. I saw Dr. Bardia is here. He will be our instructor today. Hi, Bardia. I will do my usual introduction at the beginning, and then we can get started. All right, so today we will also introduce the 2 mentors that we're going to have this week, and we'll let you know what is a good time for our tutorial and so on. Great, so as I mentioned, today is the 4th week of our workshop series for this year, and today we have Dr. Bardia Khosravi, and going forward, we will mention more about the quizzes later on as well. And as I mentioned today, concludes the phase 1 of the workshop series. Starting next week, we'll start with phase 2. And this is the schedule for this week. And here's the workshop. Just to briefly introduce you to the 2 mentors that we have this week. We have Shakufa and Ayush. And Shakufa is a graduate student in computer science at the University of Calgary. She is currently an associate machine learning developer at Atla ML. In her graduate studies, she works on computer vision and the utilization of deep learning-based methods, models to advance medical data analysis. And our second mentor is Ayush. He is thrilled to be joining Mathematics as a mentor this year, and over the years he's had the privilege to work with an array of innovative companies and research institutions focusing on applying cutting-edge tech solutions to pressing medical challenges. He is very excited to work with everyone here, and here we have our instructor today, Dr. Bardia Khosravi. And he is an MD and has 2 master's degree in medical education and public health from Tehran University of Medical Sciences. He has also been a full stack developer since he was 19, and since the pandemic, he started focusing on his research and on deep learning as a way of helping those suffering from the disease and through early diagnosis and efficient triage. And yeah, so we're very, very excited to have Bardia here today to give us the workshop on transfer learning and in medical image analysis. So go ahead, Bardia, if you want to say hi and start sharing your screen.
Hi, everyone. I'm Bardia, and thanks for the invite. I'm so excited for the workshop that we're going to have today. Okay, so let me just share the GitHub repo with you all. Then I can share my screen, hopefully. Share my screen. Hope this works. Okay, can you see my screen now?
Yes.
Okay, great. Okay, so when you open the repo, you're going to see this notebook here, transfer learning _ PyTorch. And if you click on that, then you see this link.
Oh, wait, hold on. It says you have started sharing your screen, at least on my skin. On my
okay.
Screen.
So let me just stop. That's, oh, okay. Just a moment. I think I should change screens. One moment.
Yeah, so for the audience, Bardia has shared a GitHub link in the chat, so you can go there and then see a Python notebook and click open, and then click the option that says open in Colab. Then you'll have a copy opening in your own Google Colab, and you can make a copy and start running.
So how about now?
Yeah, now I can see pretty well.
Oh, okay, great.
Yeah.
Okay, So, okay, so now I click opening collab. I think the Zoom should be okay, but okay. And if you go to the runtime option at the top and then change runtime type, make sure you're on GPU and the GPU type is T4. The other two options are locked if you're not a Colab Pro, which I'm not. But yeah, just make sure you're using GPU and then you're using a T4 instance and click save. And then at the top right, you click on connect. Then you will see shortly that now we're connected. And if you click here, you should see a GPU RAM option here. So this is the setup. Make sure you have this running correctly so that we can start the workshop. So let's talk more about transfer learning. This is going to be a pretty short workshop, and it will mostly focus on the discussion and understanding the concept of transfer learning, where it can be useful, and how we can use it in our own medical image research. I'm Bardia. I'm a postdoc fellow at Mayo Clinic AI Lab at the Department of Radiology, Mayo Clinic. And let's start. So if you've seen all the recent advances in machine learning, deep learning, and large language models, I'm sure pretty much everyone has probably tested ChatGPT. They know that it's all about pre-training. So if you are in a large institution that has a large corpus of data, then you can use, let's say, all your own data, have millions of images, you can train your model for a specific task. But usually, at least in medicine, this is not the case. I don't know if it works. Okay, this is not the case. So you're usually dealing with limited data scenarios. You have 1,000 images, 5,000 images, at most 10,000 images. And then you want to train a very big and good model that performs very well. And you want to preferably show in your research paper that, okay, this works better than radiologists. It can help radiologists do their job better, faster, more efficient, whatever. But this is very hard. And for example, in the large language models, if you've followed this field for a few years, then you know that it's the model that you saw here is ChatGPT. The part about GPT stands for generative pre-training. So you first a large corpus of data, and in some cases it might be supervised or unsupervised. We'll go to that later.
Sorry if please respectfully everyone mute yourself during the speaker's presentation. Thank you very much. Sorry about that, Bardia.
Okay,
keep going. Yeah.
Okay. And so this pre-training
I think we lost the other screen. Yeah.
No, sorry, I think I cannot. Sorry, I cannot use my video. I don't know why my Zoom crashes if I do that. So
Okay.
I only share my screen and talk
no
over
problem.
it. Yeah. So you should be able to see my screen now.
Yes.
Okay. Great. So it's all about pre-training, and in medical images, it's not different. So we need some pre-training, or it's better to say start or wait on randomly. So if you have previously trained a model, when you create a PyTorch,
Oops, I don't hear you again, Bardia. Can just wait a bit. I think probably Bardia Zoom temporarily crashed. I'm sure he'll come back. Oof, the other one crashed as well. Maybe we can, do you guys have questions for now? Do you know how to open the GitHub in the, yeah, T4 GPU, okay? He said that he also doesn't have, Bardia also doesn't have a Google Colab Pro, so that's what he's using as well. Oh, he's back. Awesome.
Yeah.
Great.
I'm so sorry about that. I disconnected all the devices.
No problem at all. It happened to me before as well. Great.
So, yeah, so it's better to start from, it's better to start from somewhere and not randomly initialize our model. And that's all about transfer learning. So we can, when you do transfer learning, you do two parts. First, a pre-training phase, and then a training phase, or fine-tuning, we call that. And the pre-training weights come from a task that might be close or might not be close to what you want to do at the end eventually, but at least it's much better than randomly initializing some weights. And then the fine-tuning part, you start with those weights as your starting point, and then tune that model to work well on your specific task. And we'll show how this one will help you. There are two different paradigms of doing pre-training. One is supervised and the other one is unsupervised. For the supervised one, you have a task. Let's say we have a large data set called ImageNet. It was introduced in, I think, 2012. And it's a large, I think 1.4 million images with 1,000 labels. And then you train a model to classify those images into their corresponding categories. And then you start with those weights. So this is supervised. You have a label for those data sets. For unsupervised, you don't have a label. You just want your model to understand some overall representation of the world or your data, and then use those weights as your starting point. And that's unsupervised. So if you're familiar with the NLP stuff, then you'll know that the GPT, or the first stage of training a chat GPT model, is just by unsupervised training. And that works just by, you give it a large text, and you say, predict the next word. And that's the generative pre-training. And this is unsupervised because you don't have any labels. You don't have to gather any labels for the images. You only have to have a sentence, and then you automatically say, this is the word, this is the phrase, predict the next word, predict the next word, predict the next word. We have something similar in the image world, and we'll get into that. But this is the overall idea of unsupervised learning. So let's cool down a little. So in this workshop, we will see how to train a model first, which will be, I think, a recap of what you did previously. Then we use transfer learning from a supervised source, and then see how it can help us and if it will help us. And then finally, we go over some resources that can help us through this task. Here, we will be using the Monai library, which I think Puriya mentioned in his previous workshop, I think last week. And then we will use that for our transformations. And finally, we will use native PyTorch code for training our model. So first, let's install what we need. Here we will install Monai, which is the library I just talked about, and Tim. So let's run this, and until this one runs, just click on run anyway. Until this one runs, we'll discuss that. So what's Tim? Tim, or Torch Imaging Models, is an open source library that has a full collection of all the latest models. And the good thing is they are all, or most of them, are pre-trained on ImageNet. So you can transfer learn at least from some source. It's not very close to medical data, but as we will see, it's very useful, and we will also understand why. Next, we do our imports. So if you are familiar, so this is OS, it's for just copying and pasting stuff or searching for in a directory. Random is a library for shuffling. So here we'll be using it for shuffling our data. Copy, just copying an object. NumPy, Torch. This is
TQDM is for creating a beautiful progress bar. TIM is what we discussed for our model. First, having a vanilla model architecture and then pre-training it, or having the pre-trained weights, better to say. Monai and some functions from scikit-learn for splitting our data and then creating, getting the ROC AUC. We download the data. For the data here, we'll be using MedNest. So MedNest is gathered by Dr. Bradley Erickson. It's an open source data set that contains more than 58,000 images. The images are very small, and that's why we're going to use them today, because the training would be much faster than using a full size, let's say 1,000 by 1,000 or even 256 by 256 images. The task here is to classify these images into 6 categories, and the categories are hand, chest CT, chest X-ray, abdominal CT, breast MRI, and head CT. And the dataset is open source, so you can use them freely here. As you see even here, this is a very large dataset. 58,000 images is a lot. And we'll work on this later, but just bear in mind, this is a full dataset, and the sizes are pretty small, and the task is pretty easy, so a human can do that very easily. It's 100% accuracy. So we at least expect the model have the same performance. So let's see. Next, we'll have some utility functions. First is a function I call seed everything. So this is for the sake of reproducibility. So that if you run this notebook multiple times, you get the same results. And at least your models are, or your trainings are seeded so that they are using the same sequence of transformations. So this is it. And if you want to seed everything, you have to seed the random module, Python. You also have this set this environment variable. Some packages use that. You have to seed NumPy, Torch, the CUDA backend, which is the GPU backend for PyTorch, and some other things. So you have to make your pipeline deterministic and avoid modules that are undeterministic. This usually happens when you're dealing with 3D modeling, but for now, we're fine. And the benchmark would be false so that the CUDA itself doesn't take any shortcuts to make your algorithm faster. And then finally, we also seed our transformations in Monai. So these are the things that you will need for now. Now, this. So if you worked with Monai, or I think if you review Puria's notebook from last week, you'll see that for Monai, we usually deal with dictionary-based transformations. And for dictionary-based transformations, we mean that we pass an item that has some keys, and each key will have a corresponding value. And we tell Monai to, okay, do this specific transformation on this specific key. This is very useful when you're dealing with multiple inputs. Let's say you want to get your images, masks, and labels, and then, for example, do some transformations on the image, do some unmask, do some random, let's say, rotation or flipping on both mask and the image. And then finally, for example, let's say, concatenate some tensors together to create the final label. So this is very useful. So to start with that, we need a list of dictionaries. So here, let's see, let's open this MedNest folder, and you see each one, there are 6 directories, and each directory will have some images. It won't open because there's large files, a large number of files. But if you just use your terminal, you can see each one contains those images that we need. So now, with this getDataDict or getDictionary function, we first get all the directories in the data directory, which is the MedNest, and then sort them to get our class names. And number of classes would be the length of that, so that's easy. So we should have 1, 2, 3, 4, 5, 6. And then we go through each of those images, folders, and just create a dictionary, an item, that contains image, which is the image path or image name, and then the label, which would be a number, and we'll go to that. And we just return that. So we'll have a list of dictionaries. There are multiple ways to write this function, so you can also have another alternative function for this. And now let's inspect our data. Oh, I forgot to run the imports, sorry. Okay. So we have 58,954 images, and the classes are abdominal CT, breast MRI, chest X-ray, chest CT, hand radiographs, and hip CT. So far, do you have any questions?
Yeah, I think they're saying in the chat it's all good for now.
Okay, great. So now we have to, for every deep learning pipeline, we need at least 3 sets: the training, the validation, and the test set. So we create those. First, we seed everything to make sure that we all have the same results, at least for the splitting. And we do a random shuffle of the data dictionary and then split this to 20% would be our test set, and the rest would be train and validation. So 20% goes to test. And then we split that to 20% validation, and the rest of this files would be your training files. So at the end, we'll have 3 sets: the train files, the val files, and test files. And if we run them, get this number. So we have 11,000 images for our test set, 9,000 for a validation, and then 37,000 for our training. It's a quick question. What is wrong with this splitting? And there's an option that you say nothing's wrong. So. Or let me ask you something else. What would be the ideal scenario to split these sets? You can type your answer in the chat box. Okay, consider the classes. K-fold cross-validation. You can do probably something like K-fold in this setting, but it's more of a training strategy rather than a splitting strategy. But okay, consider the classes is good. Okay, need similar distribution, I'm assuming, for the labels. Okay, that's good. Okay, that also makes sense. So I think, so I don't agree with the split. So you can also do 20% training as long as you have a good result on your test set. Then you would say, okay, we'll be good and our model is learning something. But if you are on a data scarce scenario, then I think, yeah, 80-10-10 is the better choice. I agree. What I usually do is I split my data into 10 folds and then use 1 fold always for testing. So that will be my last fold. And the 9 other folds would be for 9-fold cross-validation. So that's just a suggestion, but here you're right. Okay, one more important thing. So you said about the distribution of labels in different folds or different sets. I totally agree. One more thing. Here, we don't have patient identifiers, but if we had them, we want to make sure that images from the same patient goes into either of those sets. So we don't want images of the same patient going to both training and validation or training and testing. This is a link. And this is very, very important and usually missed in many papers. And we don't want you to miss that. So be careful. If you are using patient data, make sure that you are including each patient's data in one fold. Or if you're using, like me, train, validation, and test in one set. Okay. For now, we'll go with this one because it's easier. And but if you want to do 100% correctly, we want to use scikit-learn's what's the name? Based on your labels and group based on your patient identifiers or patient IDs. Okay, now we go to transformation pipeline. For our transformation pipeline, we load our image and the dictionary. Let me just share my screen again.
Yep.
Let's just share only one screen to see if this helps. Okay. Okay, can you hear me now?
Yeah, I can hear you.
Eugene, can you please, because I think there are 2 instances of Zoom.
So how about I share my screen and then you talk?
Oh, that would be good also.
Yeah. Oh, sorry. What did you want to propose?
No, that's fine.
Oh, okay.
The problem is solved. Okay.
All right. Let's see.
I even came to the lab to have a more stable connection, but maybe the problem is with my laptop.
All right. Sounds good. Let me know.
Oh, yeah.
Oh, I guess I'll need to.
Oh, yeah.
I'll need to run it again.
Run away.
The run time. Let me just check my run time. Okay, everything's good. So regarding the data leakage, let's say that you have a scenario where you have multiple images, but they're different images of the same patient. Technically, can you use the different images of the same patient? Let's say they're longitudinal data, but you put one of them into training, one of them into validation. In the case where you don't have enough patients to play with, to do your research on.
So we ran an experiment. So that's a very good point. And I think this is a compromise, especially when we're doing, let's say, prospective validation. That's a little bit tricky. But we've done a search. You can also do that yourself. We just wanted, if you know about the data set called CQ500, it is an image of slices of brain CT. And then you want to, there are labels for different kinds of brain hemorrhage. Some of them are annotated by radiologists. Some of them are annotated by an algorithm that was trained on those radiologists. And we wanted to replicate that algorithm using a YOLO model. And if you do not do any splitting, or let's say patient-aware splitting, you'll have an MAP of around, so that's the performance metric for object detection models. you'll have an MAP of around 80. And if you don't do any, no, it's not in the paper. So that's our own internal experiment. That's a fun experiment. You can also try that yourself. And then if you do patient-aware splitting using the same exact configuration, you'll only get a mean average precision of 46.
Interesting.
So this is very important to make sure you do not leak. So if you want to show that your algorithm is robust, you have to test it on totally different patients.
Right. Yeah. Well, but what if your setting is just limited, that you don't have that many patients, and then you have more than one images? Like I guess you can do some sort of compromise, some tricks in the data set for you to revive this.
It's better to have different. So if you want to do prospective, so even if you have multiple images of the same patient, different views, etc., it's always better to have them in same fold.
Right.
But if you have limited number of patients, then if you don't want to do prospective validation, that will be easy, because then you can just put some patients in the testing sets without having their images in other sets. But if you want to do prospective validation, then I think the best way is to find new patients, because otherwise your evaluation will be biased.
Yes. Yeah. So I think we can keep going. Were we here?
Yeah. Yes. So for the train transformations, let me see if I can.
Yeah. Perfect.
Okay. Great. Sorry. Thank you. So
let me just mute myself first. Great.
So here we will load an image, do some random transformations, and then finally convert the image and the label into a tensor. For the validation splits, we do the same, and except we don't do any random augmentations. And in the next cell, you can run this to see an example image. So for example, this is a head CT. You see the images have a very low resolution, but they're fine for what we want to do with them. And you can change this number to, let's say, 1777, something like that, and then run this. So this is another image. This is an abdomen CT. Well, there may be a mislabeling, I don't know. But never mind, these are the labels that we have. So for things to go a little bit faster, we'll be using Monai's persistent dataset. And for that, it will cache any non-random transformations into the disk. And then we'll read from those non-random things and then do the training starting there. Here, it might not help us improve our training speed, but if you have a large file, for example, you're loading a CT scan with multiple slices, then it will help you increase your training speed by more than 2 times after the first epoch. So the first epoch would be much slower because it's just reading from the disk and then writing a cache file to the disk. But other than that, it will be much faster. So let's run this. And then we create our data loaders. If you are familiar with PyTorch, you know that we usually set shuffle to true for our training, and for our validation and testing, we don't want to do shuffle to have the same composition of batches. We use a batch size of 128, and because the images are small, they will fit on the GPU. And to train our model, we have 3 helper functions to train and evaluate. The first one is one step. So that's a fairly simple function. You have a batch. If you remember, our data dictionary had 2 keys. So our batches will have also those 2 keys. We'll have a batch key of image and another key for label. And then if you're training, you put the model into train mode. And if you're validating, you put it in eval mode. And then you pass, there's a flag here, set grad enable, which means that if you are training, you are using gradients. If you're not tracking gradients for backward process. So we give the model we give the images to our model, and then this is our y-pred. We also calculate the loss, and we return the loss here. And if we are training, we also step our optimizer, which means we are updating our weights. And also we will return the softmax probabilities or probability estimates of our model's output. And this will be used for calculating our metric in the validation. Train model is very simple. You get the model, your train and validation data loaders, your loss function. And these are the necessary things. You can also specify the epochs, the file name that you want to save your model, and then the device, which we by default we use GPU, and then param groups. We'll get to that later at the end of this workshop. But here we define our optimizer. For all of our experiments, we use the same optimizer. Don't mind these param groups. For now, we will be using all of our model's parameters, and we have a weight decay and a learning rate that are specified, and they're all the same for the for all the experiments. And then we seed everything to have the same composition of transformations. And then we run our model for each epoch. So if you are running for 10 epochs, each time we go through the data loader, we get the batch. And for the batch, we will, so this is I in data. We go through the one-step function that we discussed and get the loss, and then append the losses to this train losses so that we have the loss for each batch. And for validation, we do the same, except that we also get the y-preds, which are the probabilities, and then add them to a list so that later we can calculate our AUC, or area under receiver operating curve. And then we print everything. And if we have a better AUC than what we had previously, we save our model. For testing, we do the same, except that it's very similar to validation. We go over our test data loader. We give the inputs to the model, and then we create a list of y truths, which is the ground truth, and this one, y scores or y preds, which are the predicted or estimated probabilities, and then we finally calculate the AUC. And this OVR, if you're wondering, this is one versus rest, because AUC is more of a metric of a binary classification. And then if you want to do one versus rest, which means that you are saying, okay, if this is the correct label or not the correct label. And you're not taking into account if the other labels are similar or not. So that's what OVR means here. So after running this, we will be able to train our model. So to train a model, we use only these 4 lines. We first get our device. So if we're using, if CUDA is available, and here it means that you're using the correct runtime, your device would be CUDA, and then you'll be using GPU. The model will be using a small model called ConvNext Femto. And ConvNext, if you know, is the most advanced convolutional-based model, and that's very good. The ConvNext Femto is the smallest, I think, member of the ConvNext family, and it's also imported from the TIM library. So we're using TIM to create a model, and the model name is ConvNext Femto. The number of classes will be the length of our class dictionary, which is the number of labels that we have. And then the in channels is 1 because we're using grayscale images. Our loss function is by cross entropy, which is used for multi-class classification. And then finally, we have this SC, we call that scratch. Best model weights is this, we train our model. So let's see, it should take around 5 minutes. Let's see if it runs, and then we can do something else in the meantime. forgot to run those helper functions. So, open question. Why do you think transfer learning works? Don't mind these warnings. These are because of the multiprocessing. Yes, this is fine. Okay, it's running fine. Okay. Like a child learning. So we're going to transfer learn from natural images. So images of cats and dogs. How would that help us defining if an image is a head CT or a, let's say, hand X-ray or chest X-ray? Or to ask it in a better way, what do chest X-rays and cats have in common? In non-transfer learning, initially. So what do those basic non-random weights have, Benjamin? That will help us. So Reza, you're saying they're simpler? You mean that there are simpler version of chest X-rays? I would argue that cats are more complicated than chest X-rays, but similar features. What type of features? Yeah, what type of features? That's the question. Lines and curves, correct. So let's see something cool. Sorry, I'll close the chat now. If you scroll down to the end of the notebook and go to OpenAI microscope. This is a cool, let's say, research experiment from OpenAI. And we'll go to AlexNet because it's much easier to understand. Okay. So the idea here is, let's say I'll use this and then use an image of it should be a cat here. Cat. Okay, good. It's not loading. Yes. Come on. Oh, sorry, let's just go back to the cat. We should wait till. So this is the overall structure of AlexNet, which was the first, let's say, large scale. We're going back to car. We work with the car. Large scale convolutional network that was used in the ImageNet competition and beats all the other previously machine learning based and non-deep learning based models. So this is a very simple model. You can also run it on your device locally. But here, this tool will help us see what are those features or what are the features that we see in a network represent. So here, if it's a car, this is the first convolution. Let's go to the second layer. And you can visualize different features from different channels or different neurons. So let's wait for it to load. Okay, so these are the things that are detected by the first channel or different channels, which are different filters. So you see most of them are just here. For example, this one is just a filter to detect oblique lines. This one is for horizontal, right? This one is with a little bit different, let's say, orientation. Now, if we go up to higher order features, oh, this is a ReLU. We don't need that ReLU. Let's go to a convolution one. Let's say here. So you see now the features are very complex. Essentially, the initial layers are edge detectors. They will let you, okay, now I see an edge of 45 degree line, and then there's another 45-degree line that is perpendicular to the original line, and then the layers deeper will say, okay, now I have two perpendicular lines that are angled. So, okay, this is a triangle or something similar, and down in the line, I mean, in the network, the deeper neurons or deeper layers will say, okay, now I have two triangles and I have a circle. So this is more of a cat's face. We don't have two triangles and one circle in a chest X-ray, but we have those edges. And these are the things that will help us when we want to train a model. So let's go back to our training. So that's the useful features that we'll have. And when you initialize everything randomly, you'll miss out these features essentially. So where were we? Okay, the training is now complete, and we have a validation AUC of 0.9923 after one epoch, which is very good. And we're very happy about that. Now let's see if our model is generalizable on the test set. As I said, this is a very special data set because it has a lot of case samples, and this is usually not the case with our own in-house training data. So after training, we have an AUC of 0.99201. Okay, this is pretty generalizable. So we have a an AUC very close to the one that we have for the validation. So at least the model is robust. And this is after one epoch. So now let's do transfer learning. And for transfer learning, we just add a flag here, pre-trained equals true, which will use the weights that are pre-trained on ImageNet. And by using this simple flag, you will have weights transferred or initialized to those same weights. The only thing that is different is the number of channels. So if you know, ImageNet has colored images. So it means that the network will have 3 channels, one for red, one for green, and one for blue. But now we're using only one channel. So the first convolution will, rather than having 3 channels, will have 1. And Tim, the package, handled this very smartly by just averaging the 3 weights into 1 weight. So that's the only thing that will happen, and the only part that will change. And also note that here, the number of classes for the original ImageNet was 1,000, but here we only have 6 classes. So this will also be changed. So the last layer will change and the first layer will change. Everything else will be initialized with the same weights. Yes, that will be very useful if we have a model that is pre-trained on black and white images, and we'll get to that at the end of this course, end of this lecture. But yeah, the point is this library is not specifically for medical use cases. And most of the people they use that, and the person behind that, Ross Whiteman, is mainly focused on natural images. So if there is an initiative to train these models on black and white version of ImageNet or other data sets, that will be very good. But I don't see any initiative out there. But there are some models out there that I will let you know of, but for now, this package, the TIM library, only has 3 channeled images, or trained on 3 channeled images. So another question, so we talked about GPT or ChatGPT and how it was pre-trained. So what unsupervised pre-training regimen can you think of for medical images or for images in general? The unsupervised or self-supervised? So in natural language processing, we predict the next token, right? So we say how, are, and then blank. So probably the next token would be you and then a question mark. So that's how usually it ends. And now for medical images or any type of images, you can draw a black box on an image and then say, fill out this part. And the model is essentially learning to, okay, these are the contexts that I have. Now, what would be the perfect fit for this black box? And this is self-supervised, better to say, because you don't need any training labels. You just draw random black circles or black squares on an image, and then ask the model to fill those holes. That's one thing you can do. There are other things. So for example, the other scheme, you can just do a puzzle and make 9 squares out of a square image, and then shuffle them, and then ask the model to guess what's the right order. This will help it to get an overall understanding of the spatial relationship of different components of a chest X-ray. For example, at the top, you'll have the ribs, you'll probably have the cervical spine, and then when you go down, you probably see the abdomen, and then the heart at the middle. So these are the relationships that we want our model to find. And these, other than having those edge detectors, will have features that are very close to what we want in our end product, which is a model that can detect, let's say, pathologies on chest X-rays. Okay, now our model is trained. So the TL is transfer learned, and the best model weights. And then we see, okay, we have an AUC of 1. We'll get to that, Benjamin. I'll answer your question now. So now let's load our model best weights after transfer learning and test it on the test set. Okay, now we have an AUC of 1, which means perfect accuracy. And okay, so not much of a difference. If you train your model, let's say, for 10 epochs, you probably get an AUC of 1 without any transfer learning. And this is very easy. So you just, on Colab, it takes 1 hour to train it for 10 epochs. Not a huge deal, right? But at least you can say, okay, with the same amount of data, I get the same performance, but much sooner with less training resources, because you eventually, or you or your institution are paying for your compute, your, let's say, data storage or whatever. And if you can get the same result in a shorter amount of time, that's desirable, and that's what you want to do. So the first thing is you get there faster. And in theory, they've shown that if, at least in medical imaging, if you are not using pre-trained weights, you get the same result, but 2 to 3 times slower. So for example, if you train your model for 10 epochs on transfer learning and get an AUC of 95, if you don't want to do transfer learning, you theoretically can achieve the same AUC, but in 15 epochs, 20 epochs. So the first thing is this. But as we said, MedNist is a very large data set. What if we have a smaller data set? So let's do this. Let's create a trained data set small and only have the first 10% of our images there. We also create a new data loader and run this. So we will train a model on the small, the 10% data. Okay. And it will be much faster than before. And let's see how the model performs on our test sets. So the model is again randomly initialized without any pre-training. Don't mind these warnings. These are just multiprocessing warnings. Okay, now the validation is done, and we have an AUC of 87 on the validation. So with 10% of data and only one epoch, we have an AUC of 87. Now let's go. Okay, the model is still robust. We have 0.87 AUC on the test set. So we are doing random initialization on 10% of the data. Now let's do transfer learning. So you know that usually the more diverse and larger number of imaging training samples you have, the better model that you will end up with. So let's go and answer those two questions. Yeah, you can also filter those warnings. Usually it won't happen if you're using your own device, but yeah, with Colab, that's fine. The other way you can just get rid of that is decreasing the number of workers to 1, which is essentially eliminating the multiprocessing aspect of this data loader, but it's not very useful. Okay, the other one. Could this be used in generative AI to make images showing specific pathologies for teaching examples? So I don't know if I get this correctly, but you mean having a generative model as a teacher and a supervised model as the student, right? If that's what you're saying, yes, and they're doing that. The point is that you have to have a pipeline that ensures your generative model is learning the useful information that is needed to characterize, or let's say create, a pathology. And this is very tricky. Okay, now with transfer learning, we still have an AUC of 1 on our validation set and an AUC of 99995 on our testing set. So at least we can see our model's performance is much better. And if we have limited data, then doing transfer learning is a reasonable decision. But the thing here is that we are getting a set of we call them useful weights, and we are just having them on a model and say, okay, now let's see what you learned from this new data. And if your two data sources are, let's say, let's have a question mark here. I'll ask you guys this one. But if they are very distinct or very close, and this is the part that you have to decide, very close or very different, then you're essentially updating those weights with the same rate. And this might, let's say, cause changing of those useful weights, those weights that are at the beginning of your network. And your edge detector might become something else, and you don't want that. So one way is either to freeze those initial layers first, or let's say the alternative is to give them differential learning rates. So your initial layers will be updated much slower than your final layers, which are those superstructures. So you don't want to change your initial features, those lines, those edge detectors, to be, you don't want to change them drastically, but you want to change your final composition drastically. So you don't want the final composition to be like, let's say, this is a cat, you want it to be a chest X-ray, but you don't want your initial edge detectors to be changed. So we can use a differential learning rate, let's say, parameter group. To do this, we define these param groups. We initialize our model, we pre-train it, we set it to pre-train so that it has the same weights as of a model that was trained on ImageNet. And then you define, okay, different parameter groups. So if it's in the head, which means the classifier, give it a learning rate of 1e minus 4. So the CommonX femto has three stages. Yes. Stage 3, stage 2. I'm missing here stage 1. Let's add stage 1 here. So it has 3 stages, and then let's make this also 7. Oh, it's changing that. Let's have. Okay. So stage 1 at the head, and then stage 3 will have smaller learning rates than stage 2, and everything else, which means the first stem and stage 1 and stage 1 would have a learning rate of 1e minus 7. So as we're going deeper into the network, we're increasing our learning rate. So the velocity of change would be much higher. And you can see this one is 1,000 times, it has a learning rate 1,000 times larger than our layers. And with the functions that we wrote, we pass these param groups as a training function. And now we can run this. This is still 10% of the data. Yes, yes. So without looking at the results, what do you think, where do you think we should use this technique? When the two data sets are far from each other, when the two data sets are very close to each other, when we have a lot of training samples, when we have smaller number of training samples. Or it can be a combination of these 4. Okay. I'll put that as an open question. You can think about it later. Okay. So here we see that our model had an AUC of 96 and about a test AUC of 96. Still not as good as what we had previously. And you should be able to guess why. My recommendation, less flexible alpha. Okay, very good. How can you increase that flexibility? Or let's say, no, let's say, why do you think we need some less flexibility when training a model? So I said, this is a good approach and you can use it. So why is that? As you said, this is less flexible. do something else. More deterministic solution. No, because when you are seeding, and if you're seeding correctly, then your results are deterministic. By deterministic, what we mean is that if I run it twice and you run it twice, all the 4 experiments will have the same results on the same machine, of course. But yes, are very far apart. And you're right, Benjamin. And you have a very, very little training data. If you do so, your model will start overfitting. So even those initial layers, rather than starting to be edge detectors, they will be, let's say, specific image detectors. So if there is a blue mark at the top right, it will be a cat. It will always be a cat. If you're training a model with 10 images, then you don't want to unfreeze all your parameters. You want to either freeze some of the initial weights or use differential learning weights for them. So 2 things I want to go over before we end and open up for questions. You can also try this, use a stage, also freeze stage 1 and give everything else. So that will be head. You don't need head. You go with straight 3, 2, 1, and the rest would be 1e minus 4. Try this one because there is a convolution at the beginning. And you can also make that more flexible. You can also write your own. So let me just add it here. Model. If you just type in your model and then run it, this is the architecture of your model in a very neat way. So this one you have convnext, which is your model class. You have an stem. So then you have stage. You have stage 0. Stage 1. Stage 2. Stage 3. Now, the other thing is, then you go to the pre-norm, which is identity, we don't need here. And then finally, the head. The head is essentially the global average pooling here. Sorry, adaptive average pooling here. And then your classifier. Your classifier head is, it gets 384 features and outputs 6 class probabilities. So you can play with this. If you know the architecture of your model, then you can just do differential learning rates on them. Finally, here are some reading resources. The first one is Middle. It's a website, a free learning resource that was developed by our lab. And a disclosure, I'm part of the author team. But I will really recommend it to go over some of the courses, some of the notebooks there. They're all free. They are on Colab. The OpenAI microscope is the one that I showed you. You can visualize the features of some of the pre-trained networks, and you can also play with some text prompts there. Those are, let's say, trained on Clip with Clip. This is a very nice paper, SSL in Medicine, Self-Supervised Learning in Medicine. It gives you a very good overview of I don't know what happened. Oh, it opened. So it gives you a very good overview of some of the techniques that are there for natural images and that can be used for medical images. So here, for example, you see contrastive learning. If you see me now and I change my t-shirt to something, let's say purple, you should see that, okay, this is the same person. And that should happen. The same thing should happen for neural networks. So if you're just changing this toy bus to, let's say, rotate it by 50 degrees or 15 degrees, then the model should say, okay, these two are the same. And this is called contrastive learning. So this is one interesting, and I think this is the state of the art self-supervised technique here. So this is also a nice paper. And finally, this RAD ImageNet. So as we discussed, all the network weights that we used here are from ImageNet, which is, as one of you pointed out, is three channels. So it's colored images and it's natural images. So it's not very close to medical domain. Here in the RAD ImageNet, I think, yeah, paper and repo, they introduce a paper, sorry, let's go back. They have the good stats here. The paper is published in Radiology AI. And you see they publicly release a large data set, I think 1.1 or more than 1 million images of different modalities. And you can pre-train your networks on them. They also have some pre-trained weights for these 4 models. And they have 165 or 69 number of classes. So they're trying to mimic what they did with ImageNet. There are some issues with the dataset, but it is publicly available. You can just email them or fill out a form in their website, and they will send you a link. But it's a very good first step. You can also play with that if you like. You can use the weights from those pre-trained weights. You can initialize those weights. There are some notebooks. So now let's see the questions. Okay. How we can work on PET-CT images if there is a resource. So you mean for pre-trained models? If you mean for pre-trained, I don't know about PETs, but RAD ImageNet has a lot of CT scans. And the point is, starting with these initial weights would be very helpful. Yeah, it has this much number of CTs, but it will be very helpful. It won't be, you still need to do some fine tuning, but at least your model is learning the contrast, the edges, and of course, those grayscale features that we really like. So with that, we're at the end of this session, and I'm open to any questions.
Thank you, Bardia.
For the freezing of the first layer, I would say if you have limited number of data and you suspect overfitting, then freezing the first or having differential learning rates will be very useful. I really don't like freezing myself, but that's a personal opinion. Don't take it very seriously. But if you're doing differential learning rates, if you have very limited number of data and you suspect overfitting, then it's a good idea to freeze or do a differential learning rate for the initial layers. Okay, and I think we can conclude the session.
Great. Thank you so much, Bardia, and especially the introduction to SSL, self-supervised learning, at the end a little bit, because our first session for phase 2 in week 5 will be specifically on introduction to self-supervised learning. That was a great introduction. If you're interested, go ahead and read the paper that Bardia has introduced. I will stop sharing the screen here. Thank you so much, Bardia, for the wonderful lecture today. Again, as many in the chat has expressed their gratitude. Just for everyone, we will start the phase 2 of the program next week, and with seminar and workshop again on the Saturday and the Sunday. And the tutorial this week, we will have Shakufa to give us the tutorial on Thursday, 2 p.m. Eastern Daylight Time. Make sure to check your time zones. So we'll see you there. And yeah, that's it. I think we have a question from Benjamin. For the quizzes, do we need to get perfect? I don't think we, Jose, I don't think we set the limit to be perfect. What was it? I think it was 75 or something like that. But I'll double check what was the limit that we set in the
quizzes are
code.
based on like YouTube videos, so I guess like 90% or yeah, because like the video is there, so
And you can always resubmit as well.
Yeah,
The
you can
Google
resubmit.
Forms are set to be resubmitting if you want to try again and all that. All right. Thank you so much. And Bardia, I just want to thank you again.
Of course, thank you all, and sorry for the technical issues at the beginning.
Oh, no
And thank
problem.
you.
It went pretty smoothly afterwards. And thank you for everything that you taught us today.
Of
Cool.
course, thank you very much.
Yeah.
Have a
So
good rest.
see you everyone next week. Bye-bye.